So, good evening. Hello, Vijay. We'll be starting today's session. I hope I'm audible. Hello. All right. I'm going to wait for maybe a minute or two if more of them are going to be joining. Thank you. No, thank you, Vijay, for the response. Okay, I'll just start briefing about what what is the portion and everything that I'll be going through. So last week we had done some discussions based on the week four's lecture modules that was taken by the instructor. And this week I'll be discussing the week five's lecture modules, that is mainly based on water quality and water pollutants, water quality parameters, what is the overall step-by-step process of water treatment, about screening and aeration, sedimentation, and certain problems on sedimentation tanks and settling velocities and all, like you would have seen in lecture 27. So it's based on this that we'll be doing today's sample questions. This will definitely help you in solving the assignment questions of week 5 that you're supposed to be submitting it by March 1st, I believe. So we'll go on to the questions. I think I would like to wait for a minute more before we move on to the questions. Hi, Sangamitra.
Hi.
So how's are you able to follow all the lecture materials on time, or is there a lag between catching up with the lecture materials? How is the course preparation going on?
Actually, I'm already in a job, so I can get time to go through all the video lectures. So I'm trying my level best, but still I don't get time, and I'm having a kid also.
Oh,
So
yes,
still
yes.
I'm trying to complete as much I can.
I think the lecture materials, the slides provided would be really useful for people like who,
Yes,
managing a job and everything. So I think that part is very useful in this case.
yes, but the thing is, if we don't hear the video lectures, then also we may not able to answer all the questions,
Right,
because
right. Absolutely
there
true.
are that is why I want to
Yes,
complete, but I'm trying as much I can.
yes, please do. I mean, there are a lot of resources like the lectures, even these questions we are discussing. Those are
Mhm.
questions that are like they're covering the major questions that might possibly come.
Mhm.
So yes, don't worry, you'll be able to figure it out.
Okay, thank you.
So I think we'll move on to the question discussions for today.
Yes.
So, like I said, it's on water quality, and it would be nice if all of you could respond to the questions. So it will be a little more interactive as well as interesting to you and me. So first, this is the first question. You can type in the chat box what might be the answer to these questions. Here we've been given the sources of pollutants and what kind of pollution is occurring. So you need to match which pollution source is resulting in this following kind of pollution. So take your time, read through it. This is also not, this is something you can actually, from the general point of view, think about an answer, even if you have not gone through all the lecture materials. Like what comes from agriculture fields, what is the what might be the main pollutant of wastewater. So the first nutrient pollution, they're talking about nutrient pollution over here. That is mainly comprising of nitrates and phosphate. The other kind of pollution is toxic and hazardous chemical pollutants, microbiological pollutants, and heat pollution. Heat pollution means increased water temperature. So what might be causing all these pollution? Okay, Vijay says it's C. Any more answers? Okay, I think I'll move on to the solution part of it. So if you see here again in the lecture materials, and if you go through the lectures, there's a table of pollutants, what is the source of pollutant and what kind of pollution it is causing. So nutrients like nitrates and phosphates, these are mainly coming off from fertilizers and pesticides and all. So the main source of this pollution is going to be the runoff from agricultural fields, like when we are using fertilizers in agricultural fields and when it rains and this rainwater flows, it will take up, wash off all these fertilizers and then flow into a river or nearby water body, and that is going to result in the pollution of the water body by the contents of these fertilizers, which most of the time is nitrates and phosphate. So the first option, the first one is going to be associated with B. Now, toxic and hazardous chemical pollutants is something that might result from landfill leachate. Now, landfill leachate is nothing but when there is a huge plot of area where all the wastes are dumped, all the plastic waste, all the food waste, whatever, like we have people collecting waste from our houses and going and accumulating it in a particular plot of area. So what happens is when it rains, this rainwater is going to go through this landfill. It is either going to seep down under the towards under the soil, or again this water is also going to flow out. So this waste is going to comprise of a lot of chemicals and which is very hazardous and toxic. So this is what is called as leachate. So second one is going to match with A. Microbiological pollution is nothing but the biological or pollution that is caused by microorganisms, unwanted bacteria and all. And this is one major, the major source is wastewater, untreated wastewater. That is the domestic wastewater that is coming from the bathrooms and toilets and all is comprising of a lot of microorganisms. So that is going to cause pollution if it is not treated properly. So the third one is going to be B. And then heat pollution is when the temperature of water increases because there's some kind of pollutant in it. This is majorly going to occur because of industrial runoff. Like when water is used as a coolant, it is going to take up a lot of heat. And if this water is directly let out into a stream or a river, it is going to drastically change the temperature at that point where it is being released. So that is again going to affect the aquatic life and all. When there's a drastic change in temperature, it is again going to cause, it is also a type of pollution. So heat pollution is associated with industrial runoff. So the option provided over here is B, which is matching with all of them. I hope you understood the association. Now the next one is, on the basis of degradation nature, water pollutants can be classified as. So from this question, you can understand there are so many bases of classification of water pollutants. Kiran has said it's A. Any more answers? Vijay, Sangamitra, Ravi, go on, just make a guess. Or if you know it, give the right answer. Okay, I don't see much answers coming up. So I'll move to the solution of this. So water pollutants are classified into certain on certain basis. And here we are talking about three kinds of natures or types of water pollutants. One which is classified based on the sources of the pollutants, from where it is generating. Next one is on the state of the characteristics of the pollutant, whether it is a physical pollutant or a chemical pollutant or a biological pollutant. And third one is what is the basis of degradation nature, whether it is getting disintegrated or whether it does not disintegrate. Based on that, there's another classification. So based on the pollutant sources, there are pollutants that are resulting as a result of industrial activities, that is industrial pollutants. Again, the one we said, heat pollution is one result of industrial pollutants. Again, there are also other heavy metals and contents that are resulting in that are coming from industries, which are also polluting water. Next one is agricultural pollutants. Majorly nutrient pollutants are falling under this category. Then there are urban pollutants. Landfill is another is coming under this urban pollutants. Then there's natural pollutants which are existing in nature itself, which when it is increased in an if it is existing in a moderate level or quantity, then it is not a problem to the environment. But if it happens to come in excess of the wanted required quality, then it will also be considered as a pollutant. And in that, there are two kinds: geogenic or biogenic. Our answer here will be on the basis of degradation. It is conservative and non-conservative pollutants. Here on the basis of degradation, yes, they have given two. Degradable is one which can get disintegrated, and non-degradable is which will not get disintegrated easily. And geogenic is, again, like I said, these are minerals that are naturally occurring, but then if it is in excess quantity and if it is affecting, if it is coming under the category of pollutant because it is imparting some harmful effect, then it is also coming under the pollutant category, natural substances. So that was the second question. Moving on to the third question. Major routes of exposure to water pollutants in humans are: how are humans exposed to water pollutants? Here there are four options given: through inhalation and dermal exposure. Dermal exposure means through the skin exposure. Only through inhalation, then there can occur transfer across the placenta. Placenta is nothing but the covering that is there when in the uterus where the fetus is growing, and ingestion and dermal exposure. Okay, there are Kiran, Sangamitra, Vijay all have told it's option D. I won't wait much time for this question. So the routes for exposure for water pollutants include inhalation. Water pollution cannot be through inhalation. That is the way through which pollutants in the air enter. So it can occur through ingestion, that is from the mouth when we consume contaminated water or some source of food that is contaminated with contaminants in the water, then it is called an ingestion type of exposure. Dermal exposure is through skin, and this can, again, while we are bathing with unclean water, this is one kind of dermal exposure. So the main route of exposure for water pollutants is through ingestion and dermal exposure. So like everyone said, the answer is D, ingestion and dermal exposure. Now moving on to the fourth question. Acute or short-term exposure to relatively high levels of contaminants is least likely to cause health conditions like. So a short-term exposure to a very high concentration of a contaminant will not cause what kind of health condition that is mentioned here. Asthma attack, headache, cancer, or eye irritation. Kiran and Sangamitra says it's C. No, sorry, Kiran says it's A. Sangamitra says it's C and Vijay says it's B. And Ravi is also there. Ravi, you can also say one answer. Okay, Ravi is not interested in saying the answer. So I think I'll go on to the solution. So acute and chronic pollution, there is two categories where you are exposed, short-term exposure to high levels of contaminants, and there's a long-term exposure to relatively low levels of contaminants. Both of these, if you are exposed to high levels of contaminants for a short time, and if you're exposed to a high level of contaminants so chronically for a long time, then it is definitely, it will cause some disease. So these two conditions are discussed over here because chronic thing is when we are taking into consideration the long-term impact of small level of contaminants that might cause health issues to us. So in short exposure, that is in a few days or a few minutes of a very high concentration of contaminant is called acute effects. This can actually result in eye irritation, and if people with already with breathing issues, it can cause an asthma attack or something like that. Chronic conditions is when a small level of contaminant which is harmful to us, we are exposed to it for a very long period of time, then it tends to it makes us susceptible to diseases like cancer and neurological and pulmonary issues and issues to the lungs and all. So cancer is one such health condition which might occur because we are exposed for a long time to a contaminant that is responsible for causing cancer. So asthma attack, headache, and eye irritation is might occur as a result of a short-term exposure to. So here short-term exposure is also called acute exposure. Short-term exposure to high levels of contamination is called acute exposure, and the effect is called an acute effect. And if it is long-term exposure, then it is called chronic condition. So just keep in mind those two words, the acute effect and chronic effect. Just familiarize with it so that if these words are coming in the question, so you need to be able to relate to it. Okay, so we'll move on to the fifth question. Which of the following is a physical water quality parameter? Pretty simple. So obviously, if there is a physical water quality parameter, there is going to be a chemical as well as biological water quality parameter. So just imagine what are the parameters which are physical. Means say that we can see something, see the quality. We can decide the quality of water by looking at it or by touching it or by smelling it. These are what is related to physical water quality parameters. So which out of these might be physical water quality parameters? Sangamitra and Vijay says it's D. And I guess that, okay, Kiran is also saying it's D. Okay, so I'll move on to the answer. So water quality assessment is done by monitoring or analyzing the water quality parameters, which are mainly physical, chemical, and biological. So like I said, physical parameters are temperature. Temperature is something that we can know by our senses. Color is something that we can see and understand. Odor is something that we can smell and understand. Turbidity again is something that we can know by, although we cannot measure it, but we can know by seeing that the water is a little dull in its appearance. It means it's turbid. Then solids, all these solids also are something that which we can know through vision and all. So this is why it is called physical parameters. Now, chemical parameters are when the chemical composition of the water is impacted, but then we are not able to visually see it. We have to do some chemical test and all to understand what is the change in the quality of water. So such water quality parameters are chemical, and biological is when the water quality is impacted by microorganisms. So temperature, color, odor, turbidity, conductivity, solids are physical water quality parameters. Chemical is the pH, hardness. pH itself is helping us understand if the water is acidic or alkaline. Then there's hardness, the presence of calcium and magnesium salts. The nutrients like nitrates and phosphates. There are metals. There are chloride, carbonates, nitrates, sulfates, pesticides, radioactive materials, dissolved oxygen. Based on dissolved oxygen, we can compute the chemical oxygen demand and biological oxygen demand, which is again going to come in the later lectures. You'll be learning more about that. MPN, total and fecal coliform, is again a test or measurable quantities of biological contaminants. So our answer here would be all of the above. Order, temperature, total solids, all of them are physical water quality parameters. So moving on to the sixth question, electrical conductivity of water is expressed in the unit of. Sangamitra said it is A. Kiran also A. Okay, this is not a question that requires a lot of thinking. Vijay also A. Thank you for the answers. So, just focusing on conductivity, electrical conductivity, it is the ability of water to carry current. So, pure water doesn't have any ions or anything in it. It doesn't have many minerals. So, it is usually a poor conductor of electricity. But then, if there are many dissolved minerals in it, dissolved ions in it, it acquires a it starts having charges in it, so it will be able to conduct current through it, and this is measured using sensors, and the unit of measurement is Siemens per meter. So here they've said that pure water is a poor conductor of electricity, and if there are dissolved salts in it, it is going to be conducting some electricity, which is going to be proportional to the amount of salt dissolved in it. So here electrical conductivity is a test of water quality parameter, and it can actually show, I mean, maybe there's a scale over here, like you see over here. This is for the pH scale, but again, we'll know if it is very bad or not by understanding the electrical conductivity that is occurring in this specimen of water. So the answer is Siemens per meter. Now, seventh question. A 10 ml of pungent water sample requires 190 ml of pure water to make it odorless. Determine the threshold odor number of the water sample. So here I can say threshold odor number is a measurement of the odor in a measurable form of water sample, and it's a very basic calculation that you require. Here Sangamitra said it's A. Very simple calculation. You just need to know how this is represented, and then you can just calculate it into 2 seconds. Okay, so I don't see much answers coming up, so I'll move on to the solution. So again, like electrical conductivity, pH and everything, order is measured using the threshold order test, and it is represented in the form of threshold order number. Threshold order number is nothing but you have the volume of the sample that we require to test, that we have to add some amount of pure water to remove that order. So what amount of pure water is required to make this smelly sample without an order will be the volume of pure water needed to remove any order, divided by the volume of the sample is what is giving us the threshold order number. So this is the formula for threshold order number, as you see here. It is a volume of the sample plus volume of the pure water required to dilute the sample and divided by the volume of the sample. So volume of the sample given here is 10 ml of order water, which is pungent water, means it's got a very sharp smell. That and it requires 190 ml of pure water to make this 10 ml of water orderless. It requires 190 ml of pure water. So totally it will be 200. That divided by again the volume of the sample is giving us this value called ton, which is threshold order number. So the answer, like Sangamitra and who else said? Okay, I don't remember. Yeah, Kiran also, Sangamitra also, Vijay also told. It is A, correct. Okay, we'll move on to the next question. Now here there are some water quality parameters and their method of estimation. So go through all of the options and select the right option. Which water quality parameter can be tested in what way? So is it microbial water quality using most probable number and volatile solids using titration? Or is it alkalinity using titration and turbidity using scattered and density of light measured? Total solids using gravimetric analysis and hardness using titration with EDTA? Total solids using scattered intensity or microbial with most probable number? Two of them are given in each option. You have to select the option with the correct pair of it. Okay, so Angamitra said it's C. Any more answers? Kiran has also said it's C. Okay, we'll move to the answer. So here are some whatever options has been given. I've just included what are the kind of test and measurements and how is it represented. So microbial water quality is done through a test called E. coli test. E. coli test, when you do add E. coli to contaminated water, the number of it increases, and then we can understand that what is the level of contamination in it, and it is or the measurement is expressed in terms of E. coli index or MPN, most probable number. So MPN is related to microbial water quality. Now, total solids is another physical water quality parameter that is measured through gravimetric method. Gravimetric method is nothing but we weigh the wet sample, then the dry sample, and then you minus the amount of water from it to know what is the total weight of the dry sample. Now, total solids will comprise of total suspended solids also, total dissolved solids also. So, total suspended solid, a method uses Wattman filter paper. It is a filter. So, whatever particles are suspended on it will remain on the filter paper, and remaining everything will go. And then it is measured to understand how much of total suspended solids are there. Total dissolved solids are again, like I said, electrical conductivity is one of the tests that is used for measuring the total dissolved solids. There are a gravimetric method can also be used. Like we have Wattman filter paper. Whatever water is going through this Wattman filter paper will comprise of the total dissolved solids. So through calculations, you can get the amount of total dissolved solids like that also. Another one approximate test is using electrical conductivity. Now, turbidity is another physical water quality parameter. In turbidity, there are two principles used for measuring turbidity. One is using light scattering principle, and the other one is using light absorption principle. So I don't think so it has been gone in much detail which instruments are using light absorption and light scattering. So neither will I go in too much detail with that. So examples of light absorption is Jackson's turbidity meter, and one example of light scattering principle is nephelometer. These instruments are used for measuring turbidity, and they are expressed in units of JTU and NTU and all, which I don't think so is required for you to study, or even if it is necessary, it will be coming in the future lectures. So here the answer will be total solids. That total solids is done through gravimetric analysis, and hardness is done through titration with EDTA. The indicator used will be areochrome black tea. So when this areochrome black tea is added to this hard water and it is titrated with EDTA, there will be a color change, blue-black color change, and that is when we can measure the amount of hardness. Again, this all will be covered in the future lectures. Yeah, so that's it. Now moving on to the next question. Question 9. Which of the following statements are true or false? Which are false regarding the aeration of drinking water, the aeration of water during its water treatment process of aeration? That is, precipitation of dissolved ions in raw water is facilitated through aeration. Turbidity and suspended solids in raw water are significantly reduced through aeration. Aeration is a major treatment process at the treatment plant for water withdrawn from groundwater sources. Okay, Kiran is saying it's B. One and three are true. Two is false. Okay. So it's option. It's okay. Then there seems to be some confusion. We'll see the solution soon. Okay. So we'll move to the solution. Sangamitra is given B. This definitely seems to be some confusion because again, Sangamitra and Kiran has been.
No, 1 and 3 are correct. Actually, by mistake,
okay. Sure. Okay, so we'll go to the solution. So aeration is a process when air is made to come in contact with water as a part of the treatment process. So what happens here is some of the dissolved gases in this will come in contact with the oxygen in the air, and the oxidation process will occur. So they are exposed to air either in the form of droplets of water, or sometimes air bubbles are provided through this water and circulated through it so that it comes in contact with air. So here, if you are looking at the correct answer, it is statement 2. It's supposed to be statement 2 and 3, because turbidity and suspended solids, when it comes in contact with air, what happens is it will form other compounds which will flock materials. I mean, it will come in contact with air, oxidation will occur, and it will start falling down. And aeration again is required for process, because wait, I'm sorry, my bad. Aeration is not helping in turbidity. So this answer is wrong. I think it is statement 1 and 3. B option is correct. That is. Oh my god, even I am confused over here.
No, actually, statement 1 and 3 are correct, and statement 2 is wrong. Because
right. You're correct. Precipitation of dissolved ions, right? So if there are any dissolved gases, those ions will get oxidized and they'll form flocks, and it will be easy for removal. And also, again, groundwater, since it is not exposed to air, there is a chance for chemicals to be there in it. So it is one major process required for groundwater. You're correct, Sangamitra. So it will be options, statement 1 and 2. So the correct answer here would be B. Right. Okay. I think I'm right? The option has to be B, right?
Since no, actually, in the question it is given which one is false.
Oh,
so right, statement 2 is false.
All right. My bad.
That
my
is why
bad.
C.
Right. Okay, correct. You're right. So statement 2 is a false statement over here. Right. Okay, thank you. I mean, I think when I confused all of you a little bit, so sorry about that.
All of us did the same mistake.
right. I'm so less. Yeah. Okay. Thank you for the for clarifying for me also. It's nice. Okay, now moving on to the 10th question. The mechanism used to determine heavy metals in water is flame atomic absorption, inductively coupled plasma, mass spectrometry, and all, or is it all of the above? Okay, I think I'll move to the answer. So here they have asked about mechanism to determine heavy metals. So in metals itself, some of the methods used to determine them are flame atomic absorption, electrothermal atomic absorption, inductively coupled plasma, mass spectrum. If you ask me what the methods are, even I'm not very sure what are the principles of the method. But I think again, it will be good to just be familiar with these terms and probably just go through and try Googling or something. Then I'm not familiar with what these methods are. Flame atomic absorption. Anyways, these are the tests that is done for understanding what is the amount of heavy metals in the water sample. So all of the above is the answer. Flame atomic absorption, inductively coupled plasma, and mass spectrometry. All of these three methods are used to determine heavy metals in water. Now the 11th question, Winkler method or Azide-Winkler method are the most commonly method used to determine what water quality parameter. Is it dissolved oxygen, chemical oxygen demand, biological oxygen demand, or all of the above? Sangamitra says it's A. Need more answers? Kiran says it's A. Okay. Okay, so there are no more answers. So the so dissolved oxygen is a very important water quality parameter, particularly when we come to wastewater treatment. But again, like I said, good quality water, the amount of dissolved oxygen is going to be more. And when the quality of water deteriorates, the amount of oxygen dissolved is going to be less, because mostly what happens is the microorganisms or whatever chemicals, if they require oxygen, they're going to take up the oxygen in the water and get oxidized. In the end, what happens is the amount of oxygen is going to get reduced in the water. So for testing this, the method used here can be Winkler method or Azide-Winkler method. traditional laboratory methods, which is used for understanding the amount of dissolved oxygen in water. Now, chemical oxygen demand and biological oxygen demand is the biological oxygen demand is again a measure of how much of dissolved oxygen has reduced. Even COD is also one measurement of it. All of this is again going to be taught in detail about how we calculate BOD, how we calculate COD, what is the relation between BOD, COD will be taken in future lectures. So the answer for this question would be dissolved oxygen. Like this is making use of a titrate called sodium thiosulfate. So when water is mixed with this sodium thiosulfate, it is going to be reddish brown. No, it is going to be yellow in color when it is mixed with water with dissolved oxygen. And then when you add the starch indicator, this color is going to change. That is the point when you will measure how much of titrate is required and calculate what will be the dissolved oxygen concentration. So the name of the method used here is Winkler method. This is also one very repetitive question that is mostly asked in all of the state and central government exams. What is the test and what parameter that it measures? And one common test is this Winkler method. So question 12. A drastic reduction in settling velocity is typically observed in which zone of settling? So from here you can understand there are 4 types of settling. And these 4 types of settling are occurring in 4 layers of the water treatment process. When you're talking about settling, it is definitely going to be the sedimentation chamber. So what type of settling will result in a drastic reduction in the settling velocity? Says it's B. Okay, I'll move on to the answer. So there are 4 types of settling, like I said. First is the discrete settling. Second is a flocculent settling. Third is a hindered settling. And fourth is a compression settling. Okay, got one more answer. Sangamitra also says it's B. But here, as you can see, the first type of settling is occurring when low solid concentration is existing, and particles will settle without any interactions. So this is called discrete settling. In type 2, the flocculated particles are going to increase in size, because of which they are going to again settle faster. In hindered settling, these particles are going to impact the settling of other particles. So if through collision there's some energy reduction, and what will happen is because of that impact, the settling is going to be a little more restricted. And in the fourth type, again particle concentration is so high that again maybe because of collision or some inter-particle mechanisms, the settling is going to reduce. I mean, the velocity is going to reduce. So it is in the last type 4 type of settling that the settling velocity is going to drastically reduce. Second one, the settling velocity is going to increase more than the discrete type of settling. So this is also a nice question, a confusing type of question where you need to understand a bit about what kind of mechanism is occurring in what type of settling. So the answer for this question would be type 4, compression settling. Type 1 is discrete, type 2 is flocculent, type 3 is hindered, and type 4 is compression settling. I don't know why they put the C option as the 4, maybe again to confuse. So like we had got confused in the earlier, which is not and which is, maybe giving more attention to the options and the question and simple terms like that can help us not lose a mark. So this is the answer for this question. Question 12, type 4, compression settling is what reduces the settling velocity of a particle drastically. Now here the 13 to 15 question is numerical. I would like all of you to take time and try it, even if you don't know the methodology. It can be done because there are units based on it's all based on volume, area, and everything. So please give it a shot. Maybe I can also give you the formula that is required. So this question here is talking about a 5-meter deep clarifier. Clarifier is nothing but a sedimentation tank in a water treatment plant. It is required to treat 25 million liters per day of raw water. Now, volume of the clarifier is given. The depth of the clarifier is also given. Volume of the clarifier is also given. Its length to width ratio. That is the length, the horizontal length and the width of the ratio is given. Now, they have also given the density value, which is 10 to the power minus 3 Newton second per meter cube, and the dynamic viscosity of water, which is 1000 kilogram per meter cube, and the specific gravity of the particles which are there in the settling tank, which is required to be settled. Now, what are you supposed to find is the overflow rate. I can explain you what is the overflow rate, and then you can maybe try doing the question. You require to determine the overflow rate. You require to determine the diameter of the particle, not only the diameter particle, that diameter which can be removed with 100% efficiency, and also the horizontal velocity of the particle. Now keep all this, man. We have been given the depth, we have been given the volume, we have been given the length to breadth ratio. We have been given how much of water is being treated per day, the density, dynamic viscosity, and specific gravity of the particle that requires to be settled. Now, there are few procedures or formulas that you require for this question. The first one is, what is overflow rate? Like if you see at the bottom of the slide, they have given a definition of overflow rate, which is the volume of the water that is flowing in a unit time per unit surface area of the settling basin is known as surface overflow rate or an overflow rate. So if you see here, if this is a three-dimensional view of the tank, you can see per unit surface area. If this is if this area is at 1 in meter square, if it is through 1 meter square of area in 1 second or 1 day, how much of water is passing through this is given by the surface overflow rate. Now, this is a design criteria for that required to design a settling tank. So the definition of surface overflow rate, which is the first question which we require to find out. What is the overflow rate of the tank? And you can see here, it is given by the overflow rate is equal to Q by A. That is, whatever discharge is coming into this. You can see Q over here, Q by the area of the tank. Here, the area of the tank meant by them is the surface area, the top area of the tank. So this will give us the overflow rate. And if you notice here, the units are meter cube per meter square per second. Now, if you cancel this, you will finally get a value of meter per second. So ultimately, this is the unit of the term that you need to get. Now let's go back to the question and calculate the surface overflow rate. You can please do it. So this would be a good exercise for you. And there are more problems that are coming in this category itself. So go back to the question and you can do it. So this is a question over here. Just try doing it and giving the answer. It will be good. A good exercise. So they have asked you to find the overflow rate. And the overflow rate is going to be in meter cube per meter square per day. Like I said, it is the discharge divided by the area. We have the discharge over here. We can also calculate the area over here. The data is there. So just calculate the first question's answer and please let me know. Is anyone doing? Sangamitra,
Yes,
Vijay?
yes, I'm trying.
Yeah, sure. Just confirm. Sangamitra, when you're done, just pick the answer and then we'll move on, okay?
Yes.
So this is the answer for the 13th question, right?
Yes.
Okay. Should I wait for anyone else? Is anyone else doing? Ravi and Vijay, shall I move on with the answer discussion? Okay, so I'll just go on. So, like I said, here the overflow rate is the volume of the water that is flowing in unit time per unit surface area of the settling basin. Now, this is a design quantity. Now, if you see over here, like I said, correct answer is 500. So flow through the clarifier is been given as 25 into 10 to the power 3 meter cube per day. That, and they have given also the depth. So if in order to get the area, we can divide it by 5, which is the depth that is provided, which is giving us 50 meters square. And by simply putting into this formula, velocity is equal to Q by A, you will get the answer 500 meter cube per meter square per day. Now let's move back to the question. Next question is, determine the minimum diameter of particle that can be removed with 100% efficiency. So two quantities are given importance here. The diameter of the particle that needs to be removed, and also it has to be removed with 100% efficiency. That means all of the particles that are coming in should be removed. Now, this is where we have quantities, terms like settling velocity that is coming in. Now, settling velocity is nothing but the velocity with which the particles settle down under the action of the gravity. Now, there are certain conditions for this. Settling velocity follows the Stokes law that assumes that the diameter of the particle, or the particle is a spherical particle. Although the particle is not actually spherical, we are in Stokes law, they are assuming that the particle is spherical in nature and it is moving down. And the velocity of the particle is given by this formula, which is settling velocity is equal to acceleration due to gravity into the density of the particle minus density of water into d square, which is the diameter of the particle that is being settled, which is what we are supposed to find over here. The 14th question is to find the minimum diameter of the particle that can get settled. divided by 18 mu. Mu is dynamic viscosity of water. So I have given you two more other formulas. What all these formulas are related to this only. Now, if this formula is giving us the settling velocity in terms of dynamic viscosity and density, this formula is converting this density into specific gravity. Now, specific gravity is the value that has been provided to us in the question. If you see here, they have given us the specific gravity of the particle. Now, what is specific gravity of the particle? Specific gravity, Sangamitra, do you know what is specific gravity of particle? It's okay if you don't know also, just to know. Okay, specific gravity of the particle is nothing but the density of the particle divided by the density of water. So density of water is considered a standard. Density of the particle is compared to the density of water, and that ratio is called the specific gravity of a particle. So here what happens is when density is converted to specific gravity, you are multiplying by density of water. Can I rotate and show? You are multiplying this equation with G into the rho W and dividing this equation by rho W. You're multiplying, dividing by rho W. What happens here? Rho P by rho W is equal to G, and rho W by rho W is equal to 1. So that is how this term we are getting. Now you can also see here it is given dynamic viscosity, but here it is another term which is called as the kinematic viscosity. So this equation, it can be used when we are given with the density of the particle and the dynamic viscosity of the particle. This equation can be used if the specific gravity of the particle is given and the kinematic viscosity. Now kinematic viscosity nu is equal to dynamic viscosity mu by rho. Viscosity is a property of water. Kinematic viscosity of water is equal to dynamic viscosity of water divided by rho W. So what is happening here is they have converted this rho W that is going to be in the numerator. Here somewhere if rho W is coming, then this mu divided by rho W is equal to this kinematic viscosity. So that is how this formula is coming. Now this is the formula that we earlier discussed. In terms of dynamic viscosity, here mu by rho W into G, specific gravity, minus 1 into d square by 80 is the formula for settling velocity. And so in order to do the next problem, we have to know this equation. Settling velocity of the particle is equal to G into specific gravity minus 1 into d square by 18 mu, or if you want to convert mu to kinematic viscosity, you have to multiply, divide the dynamic viscosity with density. If you want to convert the density to specific gravity, you have to divide the specific gravity of the particle with the density of water. So these are the formulas that we use to find out the settling velocity. Now, not only that, under Reynolds condition, there's another condition also for which this equation can be used. That condition is when the Reynolds number is less than 1. That is indicating that the flow condition is laminar in nature. So Reynolds number is this value. This value is given by rho Vd by mu. Rho here is the density of water. V here is the velocity of the particle. D here is the diameter of the particle divided by again the dynamic viscosity. If this value is less than 1 only, we can use this formula. And if this value is less than 1, the drag coefficient over here, drag coefficient is one other force that is acting on the particle, is given by 24 by Re. Now let's move back to the question. So here they have asked us to find the minimum diameter of particles that can be removed. That can be done using the equation that I just now told, the settling velocity equation. And here they have given all the terms that is required. Dynamic viscosity, which is mu, is equal to 1 into 10 to the power minus 3 Newton second per meter cube. Specific gravity of the particles is 2.65. That information we have, we can actually, if we have the settling velocity, we can know what is the diameter. Now, what is efficiency they are talking about? Let's move on to that. So efficiency over here is a condition where all of the particle that is entering is going to get settled. Now, when water enters a tank, whatever particle is entering will be in multiple size. There will be small particles, there will be medium sized particles, there will be large sized particles. So all of them are going to settle with different kind of velocities. Now, in order to know what percentage of the particles that is entering the tank is going to settle completely is why we need to understand what the settling efficiency of the tank is. Now, for that purpose, what we do is we calculate a critical speed, that is a threshold speed with which we can compare the settling velocity. Now, how is this threshold speed or critical speed calculated? It is calculated by dividing the depth of the tank. Divide the depth of the tank divided by the time with which the particles that falls down is giving us the detention time of the particle. Now, detention time of the particle, how is it calculated? We can calculate T by dividing the volume of the tank by the discharge rate. So if we know the discharge rate of the water that is entering the tank, and if we know the volume of the tank, if you divide volume by discharge, you get the detention time of the tank. That is, this tank particles required to stay in water for this much time if it has to get settled. So that is the design criteria of the tank that is being used here. So the depth of the tank divided by the detention time will give us the critical speed. Now, if this critical speed should be the surface overflow rate, that is, when we are designing a tank, we should design a tank that is having an overflow rate equal to this critical speed. So only then the particles entering will settle. Now, we don't know what type of particles are going to enter this tank. So we will calculate the settling velocity of the particle. Now, if the settling velocity of the particle is greater than the critical speed that is required in the tank, then it is for sure all the particles will settle down. But if the settling velocity of the particle, that is, if we know the diameter of the particle and we are calculating the settling velocity, if it is less than this critical speed or the surface overflow rate, then it is not going to settle 100%. I hope everyone has got an idea of what I told just now. So these are all design criteria for a settling tank, where first we need to calculate the surface overflow rate. That surface overflow rate is giving us a critical speed with which the particles should settle in the tank. Then we'll calculate the settling velocity of the particle. If the particle is settling with a velocity greater than the velocity with the critical speed of water entering the tank, then that particle is sure to settle. But if it is entering with, if it is traveling with a velocity less than the critical speed required for the tank, then it is not going to settle completely. So now we will move back to the question, which is asking us to find the minimum diameter of the particle that can be removed with 100% efficiency. So what we do here is we have to calculate the settling velocity. Now, in order to calculate the settling velocity, we need the diameter of the particle. So here they have asked us to find the diameter of the particle that can help us in removing with 100% efficiency. So what does that mean? It means that the settling velocity should be equal to or greater than the overflow rate. Only then we will get 100% efficiency. So here we have calculated the overflow rate, that is giving us the critical speed of the tank. Settling velocity should be at least equal to it. So what we will do, for the settling velocity, we will use the overflow rate. We have the velocity here, we have acceleration due to gravity, we have density of water, we have dynamic viscosity, we have specific gravity. By putting it in that Stokes' laws equation, we can find out the diameter of the particle required. If anyone have you got an idea of what I said just now, then it would be good for you to calculate find the solution for this question. Will you be able to do it? Do you want me to move on with the solution, or would you be trying to do it? Is anyone trying to find out, or should I move on with solution?
I'm trying, but confused regarding the units actually.
Okay. So shall I wait for you to finish the answer?
No, you continue.
Okay. So here, like I said, they have asked to find the minimum diameter of the particle with which the particle with that has to be there, so that the settling will take 100% of settling will occur. Now, for that, like I said, we have some quantities. Using this equation, we can find out the diameter. So this is the solution. The flow through the clarifier, we had found out it is 25 into 10 to the power 3 meter cube per day. Area we found out, and we found out the overflow velocity, which is this 500 meter cube per meter square per day. Now, using that is equal to 500 meter per day, because if you cancel out the units, meter cube divided by meter square, you are going to get meter per day. All right. So we have the velocity over here, the critical velocity, which is equal to the surface flow rate, which is 500 meter per day. If that is converted to meter per second, this is the value we are getting. Now, like I said, what was the condition for 100% efficiency to occur? For the condition for 100% efficiency to occur is the settling velocity of the particle should be equal to or greater than the settling the critical speed of the tank or the surface overflow rate. So this is the condition over here. This is the condition over here. Sorry. This is the condition over this is the condition over here that is that needs to be fulfilled. So in place of the settling velocity, we have already the surface overflow rate. So we'll put the 500.005787 value in here, multiplied by using this formula. Density of water into G into surface specific gravity minus 1 by into D square divided by 18 mu. So we have the density of water, which is 1000 kilogram per meter cube. Acceleration due to gravity is 9.81. Specific gravity is 2.65 minus 1 into D square. We are supposed to find divided by 18. Kinematic viscosity, they have given us 1 into 10 to the, sorry, dynamic viscosity, they have given us 1 into 10 to the power minus 3 Newton second per meter, Newton second per meter. And that value is put here, and this is the answer we'll get. We'll get it in millimeter, 0.080221 millimeter. Again, we should be careful about the units. Here we are using in kilogram per meter cube. This is also in meter per second. The value of D you will get it in meter, that you need to convert it to millimeter. So always be careful about the unit in which they require the answer it, because particles are going to be really very small. So if you put it in units of meter and all, it is going to be it won't look nice. So here also you are finding D square, not D. So at the end of the calculation, it is necessary that you take it under root. So these are things that you need to be keep in mind when you use this formula for settling velocity. If the velocity is given, you should find the diameter and then take the square root of it in order to get the diameter of the particle. And another thing that you have to be careful about here is the specific gravity and density relation between specific gravity and density of the particle. Specific gravity is the density of the particle divided by the density of water. Another relation you have to be aware over here is the relation between kinematic viscosity and dynamic viscosity. Kinematic viscosity is equal to the dynamic viscosity divided by the density of water. Another condition you have to be aware about here is the relation between settling velocity and surface overflow rate. If the settling has to happen with 100% efficiency, the settling velocity should be equal to or greater than that of the surface overflow rate. Only then full particles that are entering, that size particle which is entering, will settle. Now the 15th question was to determine the horizontal velocity of the particle. Now settling velocity is a vertical, that is how it will go down and settle. Now they want to find what is the horizontal velocity of the particle and water in the tank. With what velocity is water flowing through the tank, and that velocity is going to help in carrying the particles across the tank. Ideally, we require that the particles settle, but anyway, since it is entering the tank and the water is going out, it will also have a horizontal velocity. Since it's a vector quantity, you will have a vertical also, horizontal velocity also. So here they are asking us to find the horizontal velocity of particles and water in the tank. Now, how do we calculate that? Now, for calculating that, what information we'll require? We'll require the length of the tank, because the water is going to travel like this and go out. So we'll require the length of the tank. But here we have only been provided with the information that the length to width ratio is 4.5:1. So here what information is given? Length to width ratio has been given. Usually for tank dimension, length to breadth ratio will be given, and here it is given as 4.5:1. So how do we get the surface area from that? So we already got the area over here, 50 meters square. So we know that the 50 meters square length into breadth is giving us the 50 meters square. So here the 4.5 into the breadth will give us the 50 meters square. So for 4.5 meters of the length, what amount of breadth is going to give us 50 meters square? We'll get it by the simple calculation, which is 50 divided by 4.5, giving us 3.3 meter, this portion of the question. So now if we know the surface area, now in order to calculate the horizontal velocity, we have to know the surface area of the tank. I'm sorry, there's a confusion over here. Yeah, we need the length and the depth of the tank. Now we want the water to be traveling in the horizontal direction. So the dimensions that are of importance over here is the length of the tank and the depth of the tank. Since water is going to go like this, we have to know the depth of the tank and length of the tank. So here we have the depth also, we have the length also. We are going to divide the flow rate. Flow rate is being given as 25 into 10 to the power 3 divided by the breadth we got here, 3.3. Oh no, there's some confusion in that.
No, it is right. Actually, length is to breadth is 4.5:1. So length equal to 4.5 times breadth.
Right.
So in area equal to length into breadth. So in place of
L,
yeah, we can put 4.5b. So 4.5b square. This 4.5b into b equal to 4.5b square.
Okay. No, but I'm talking about the horizontal velocity over here. So no, horizontal velocity, we need the length and the
we need depth. The breadth and height, because it is
right.
horizontally. It is perpendicular to
the flow area.
Yes,
right. Yes, you're correct. You're right. It's okay, Kiran. You want something? In the end of the session, we can discuss again if you want anything. So you're right, Sangamitra. So it is flowing through the cross section. So cross-sectional area is what we require. So for cross-section, you need the breadth and the depth. So we have the breadth value over here and we have the depth value over here. Let me make this. So if you see the tank over here, this water is going to go like this. So we need the cross-sectional area of the tank, that is the breadth into the depth of the tank, and for that purpose we got the breadth and we are dividing the breadth into depth with the discharge, and that will give us this value of velocity. So this is going to be the horizontal velocity. So this problem is one standard problem that is always asked. Discharge will be given, volume discharge rate, that is meter cube per day, meter cube per second, whatever is the rate will be given, volume of the tank will be given, depth of the tank will be given, area ratio, length to breadth ratio will be given. They will give the specific gravity of the particle that is going to enter the tank, dynamic viscosity or kinematic viscosity, either of the values will be given. We will have to calculate the settling velocity, we will have to calculate the surface overflow rate, horizontal velocity, and what is the diameter of the particle with a certain settling velocity, and with what efficiency it is going to be settled. So these are some of the important formulas that you need. This condition is one important condition that you need to keep in mind. Settling velocity of the particle should be greater than or equal to the surface overflow rate, then only you get 100% efficiency. And this formula, the Stokes laws formula, which is giving us a settling velocity of the particle, and the surface overflow rate formula, that is giving us the discharge rate divided by the surface area, which is breadth into length. Now that was the 13 to 15 question. Now again we will do one question which is related to this. I think Sangamitra, if you got a grip over it, you can try this question. There are more questions that are coming. If you do it again, you can practice here. So in here, yeah, an ideal horizontal flow settling basin. Again, a tank is given, the depth is given, surface area is already given, rate is given as 8,000 meter cube per day at a temperature of 20 degrees Celsius, when the density of water is going to be 1000 kilogram per meter cube. Assuming Stokes law to be valid, that is, we can use that formula of settling velocity, proportion percentage of spherical sand particles of this much size diameter with a specific gravity will be removed. What is the chances of it being removed? Percentage of spherical, that is, they're asking for the efficiency over here. So in order to know the efficiency, we should know two quantities. One is the settling velocity and one is the surface overflow rate. I think pretty easily we can calculate the surface overflow rate. Using the Stokes law, we can calculate the settling velocity, because they've given us the diameter of the particle, specific gravity of the particle. This is the dynamic viscosity. This value over here is, giving us the dynamic viscosity. Unit is wrong. It should be Newton second per meter. This I had given the dynamic viscosity unit over here was wrong. It is kilogram per meter second, not kilogram per meter cube. So Sangamitra and the others, when you want me to go on with the answer, just let me know. Kiran's okay. Sangamitra, shall I wait?
Yes, I'm doing, but you can continue.
No, if you want me to wait, I can wait. I'll wait for maybe one or two more minutes and then I'll move on to the answer.
Okay.
Okay, I think I'll move on to the answer. So here again, let's take up the values that are given. The depth is given, surface area is given. So we can get a volume from this. Now water flow rate is also given. They have given the dynamic viscosity and the density of dynamic viscosity and density of water, the diameter of the particle that is entering the tank, and the specific gravity of the particle. What they are asking here is the efficiency with which it will be removed. So here again, they have said that the particle is following Stokes law. So we can say the settling velocity of the particle using this formula GD square by 18. Here they have represented it in kinematic viscosity, which we can represent in dynamic viscosity because we know the density of water. So it is GD square by 18 mu into the specific gravity minus 1 into the density of water. So acceleration due to gravity g is 9.81 meter per second square. Specific gravity is given. Diameter of the particle is given as 0.01 millimeter. Now we should be careful because here we are going to get the answer in meter per second, but the diameter is given as millimeter. So we should always be careful that we convert it to meter before substituting it in the formula. and then dynamic viscosity is given. We can either find the kinematic viscosity and use in this formula, or we can directly put it in this formula that I've shown. This formula, the second formula that is being shown here. If we have the dynamic viscosity, we can use in this formula, or we can also do it this way. We can convert this value to kinematic viscosity. Here they have done that, but it's not necessary we follow this method. We can actually directly substitute the kinematic viscosity and do the problem. So then they found out the settling velocity by substituting g value 18, 2.65 minus 1 into the d square is, again, like if you see here, it is given in mm. So they have converted it to a meter and taken the square of it. Also, always remember to take the square of the diameter. Don't forget that formula. Divided by 10 to the power minus 6 is the kinematic viscosity. Now they got the velocity of the settling velocity as 0.899 into 10 to the power minus 4 meter per second. Now we are supposed to be calculating the surface overflow rate. Now surface overflow rate is given by the Q by the area of the tank. So Q here is 5000, given a spot value. Q water flow rate is 8000 divided by the surface area of the tank is given as 900. So if you do that also, we'll get the V naught value. Here they have found out the volume of the tank by water flow rate, which is giving us a settling time. That is, volume of the tank is surface area into depth divided by 8000 is giving us the settling time. The depth of the tank by settling time they have divided the depth of the tank by the setting time or the settling time and have got the overflow rate. This actually you can calculate by doing the overflow rate also. Here you can just divide the discharge divided by the surface area, and that will give us a surface overflow rate. So settling velocity divided by the surface overflow rate is giving us the efficiency with which the particle will settle. Now removal efficiency is going to be that minus this value. So if we know the efficiency with which the particle is getting, I think I'll do the calculation over here. That will be more useful. Or did you understand, Sangamitra? Did you understand? I don't have an option to write the calculation here. Otherwise, I would have done that. I'll do one thing. I will do it in the alternate way that has to be done and put it in the slide. Just do it on your own. All of you just do it on your own also, by using the overflow rate. This is another way of doing it. We are finding the settling time. That is the volume of the tank divided by the surface of divided by the rate, which is giving us with how much of time is required to settle the particles, which is 8.1 hours. And then by dividing by the settling time will give us the settling velocity. This is another way to get the settling velocity. So that divided by the settling velocity that we have calculated, this is the settling velocity that is required for the tank, is giving 87.5, which is the removal efficiency. This one you can try it on your own in a different way and see if the answers are matching. I will also put in, when I upload the slides, I will also include that alternate method and publish the slides. So moving on to the next question. A water supply board is responsible for treating this much water. Now again a settling tank is there, that is indicating an overflow rate. V naught is equal to 20 meters per day for a depth of 3.1 meter. We need 2 circular settling tanks in parallel. What is the diameter of these settling tanks required if we want to remove? Here they have asked for the diameter of the tank. So we have a total rate. We have already one tank, but then we want to separate it into 2 different tanks. So how do we get the diameter of the tank that needs to be constructed? I think this will be a little confusing to you. So I'll just move on to the answer because I'm running a little bit behind time also. So here what they're asking is the area of the settling tank required is 75 meters square. How they got is they divided by the discharge rate divided by the surface overflow rate is actually giving us the area of the tank that required to be built. Now here also we require that same area. We don't require the same volume. So you have to, what you need to think about here is the important parameter for a settling tank is the surface area of it and the depth. It's not the volume of the tank in general. So if you have a particular surface area only, we will get a particular overflow rate, and we can compute and with that overflow rate only we can decide how much is the tank capable of settling the particles. So if you get the area over here itself, just divide that area by 2. So each tank should have an area of 37.5 meters square. Since here it is a circular tank that is being talked about, we are going to use this formula pi d square by 4 to find out the diameter of each tank that is required to be built. So again, in a settling tank, what is important is the surface area. That is what is going to decide how well the particles are going to get settled by calculating the surface overflow rate. So once you go through the lecture and you go through all these problems again and again, you will be able to familiarize with this surface overflow rate, settling velocity. All these terms will get familiar once you do all these problems. It is sufficient if you do the problems that have been discussed here itself. And also in the lecture, professor has provided some practical problems. Just go through all of that, and that will be enough for you to get familiarized with these terms. This all one value will be given, find the other value, so it is not going to be really difficult. Now this question, again we'll go to some theoretical question. Some of the non-toxic metal that is normally found in natural water are arsenic, lead and mercury. Here they are talking about non-toxic metal. There are toxic metals and non-toxic metals. So what we should know about here is what are the toxic metals and what are non-toxic metals. So what non-toxic metals are normally found in water? Not pollutants, but are normally found in water. So arsenic, lead and mercury, calcium, sodium and silver, cadmium, chromium and copper, iron, manganese and magnesium. I think this is a pretty B or D. Okay. D. Vijay said it's D. Okay, I'll move on to the answer. So non-toxic metal normally found in natural water are iron, manganese and magnesium. So there are certain minerals that is required by the body for a fluid balance and not for whatever growth that we require. So they are mainly classified into 4 groups: macro minerals, minerals that are required only in trace amount. Again, this is subcategory of the trace amounts, and there are toxic metals. So macro, that is with respect to how much the human body requires. This is not any other classification. This classification is based on our human body, what minerals our human body requires and how much of it requires. So macro minerals are those which are actually required in large quantity, like calcium, magnesium, sodium, potassium, phosphorus, iron, copper, zinc and sulfur. These are minerals that are required in large quantities in our body. Now, minerals like chromium, selenium, boron, bromine, all of these are required only in a trace amount in our body. Again, even less than that is minerals like fluorine, arsenic and everything that is required in a body. And what our body should never contain is beryllium, mercury, lead, cadmium, aluminium, antimony, bismuth, barium, uranium. All these metals are which should not enter our system, which is very toxic to us. Again, some of the minerals discussed over, like fluorine. If excess quantity of fluorine is again there in a body, we will have some diseases. If fluorine goes in less amount, then also we will, fluoride goes in less amount, we will get some diseases. Arsenic also in high quantities, it is going to be harmful to our body. But again, in small quantities, it is not going to do harm. But essentially, what we require are minerals like iron, manganese, and magnesium, which are non-toxic to our body. Now, next, another question. Most important water quality parameter for domestic use of water is. Here, the highlight is domestic use of water. What is the most important water quality parameter for domestic use? Includes bathing, cooking, washing, drinking. What water quality parameter should give? Let me just say C. Any more answers? Kiran also says it's C. Okay, go on. So again, like you guys said, it is correct coliform. That is, our main requirement should be that it should not have any microorganisms. That is going to give us diseases like cholera and stuff, contaminated water. So the most important water quality parameter for domestic uses, a check on the coliform group of organisms. Now, hardness of water is directly measured by titration with ethylene diamine tetracetic acid. It is EDTA, not EOTA. Sorry for the error. What is the indicator in this case? This is the titrant. What is the indicator in this case is the question. Yeah, Sangamita said it's A. I had discussed it, I think, in earlier slides or not. Okay. Shall we move on to the answer? So it's correct, Ariocom black tea indicator. Now there are titration based tests to understand what is the quality of water. So hardness is done using EDTA as the titrant and Areochrome black tea as the indicator. Again, here you can see methyl orange indicator. This is used for detecting the pH levels of water. And also phenolphthalein indicator is used, another parameter, another indicator for pH. This will help us in knowing if the water is alkaline or not by when it changes color to pink. So hardness here is measured using titration method, using a titrant EDTA with Areochrome black tea as an indicator. This is also one very common question that comes up in a lot of exams. So something that you should for sure know. Okay, another numerical. A town has an existing horizontal flow sedimentation tank. Overflow rate is given. The surface overflow rate is given as meter cube per meter square per day. And it is desirable to remove the particles that is having a settling velocity of 0.1 millimeter per second. So here they have given us the overflow rate also. They have given us the settling velocity also. If the tank is an ideal sedimentation tank, what percentage of particles is removed from the tank is the answer. This is a direct substitution question. You may try it. I'll give 1 minute. Only thing you need to take care over here is to change the units because surface overflow rate is given in meter per day, settling velocity in millimeter per second. So whatever is it, make the units same and then you can get the answer. Okay, this is a pretty simple question if you had understood the concept that I discussed earlier. Here again, overflow rate is given. It is 17 meter cube per day per meter square. This is nothing else 17 meter per day. That is converted to millimeter per second, because the settling velocity provided here is in millimeter second. So it is converted to that value. You will get 0.196 millimeter per second. We know the settling velocity. I had discussed when the settling velocity Vs is greater than V naught, only settling will occur. So Vs by V naught is actually giving us the efficiency of the tank, or the removal of the percentage of the particles removed. So Vs by V naught into 100 will give the efficiency of the tank, or the percentage of particles removed, which is the answer we are getting is 51%. So in the solution here, this is the option that is closely related to the answer that we are getting. So it is 50%. Another one is again similar to the questions that we discussed earlier. A settling tank in a water treatment plant is designed for a surface overflow rate of 30 meter cube per meter square per day, assuming the specific gravity of the sediment particles as 2.65, density of water as this one, dynamic viscosity of water as this one, and saying the Stokes law is valid. Why here they are mentioning Stokes law is valid is actually Stokes law is valid for laminar flow, and laminar flow happens when the Reynolds number that I discussed earlier, rho v d by mu, is less than 1. So only for such particles the Stokes law is valid. So that is why they keep, if the Stokes law is not valid, settling velocity is calculated using another formula for which you need the drag coefficient and all. So that is there in the slides material, lecture materials. If you go through it, you can read about it. So here they have said Stokes law is valid. So whatever equation we had used till now is enough for calculating the settling velocity. Again, like the first question that we had discussed in this area, they're asking for the diameter of the particle that needs to be removed. Again, we have time. We have 15 more minutes. So I'll give you some few minutes for you to try this question. I don't think so there's anything after this. So yes, you take some time and try solving this question. Okay, then if you have any doubts, you can ask. You know, wait till session ends. We have like 15 minutes more. So if you have anything, you can ask. Or I'll be uploading it soon, so you can go through the slides and the lecture material.
I'll try the question myself and post.
Cool. Yeah, sure. Okay, so I'll move on to the solution part of this. I hope nobody wants me to wait. I guess I think I'll move. So like we had earlier discussed, here the surface overflow rate is given as 30 meter cube per meter square per day. Specific gravity is given, density of water is given, dynamic viscosity is given. Minimum size can be obtained by calculating the settling velocity of that. So in order to get settling velocity, we are taking the settling velocity is equal to the surface overflow rate. Why? Because that is when we get 100% efficiency. So since we have the settling velocity, we are going to use that value over here. And you have to take care that you have to convert this value to meter per second, because this value here is in meter per day. So in order to convert to meter per second, we have divided this value by 24 into 3600, and this is the meter per second value that is given. Again, here they have converted the dynamic viscosity to kinematic viscosity, which is not necessary. You can directly use the dynamic viscosity in the denominator and multiply the density in the numerator and find this answer. Same thing will come. They got the diameter value in meters. Again, it is necessary that you convert it to millimeter, because the answer over here is provided in millimeter. So you should not stop the answer by just getting the meter thing. You should be careful to convert it to millimeter and then choose the answer. So these are some of the points that you need to focus on: the surface overflow rate, settling velocity, what conditions is Stokes law important, Stokes law's formula, what is the removal efficiency or efficiency of a tank, what is the relation, again the relation between kinematic viscosity and dynamic viscosity, and how to use it in formula. The units, you have to be very careful. Often units are going to be in meter per day, millimeter. So you should always convert it to the, majorly when in my experience, whenever I do problems like this, my major fault comes in directly substituting and not converting it into the appropriate units. That is where I always make mistakes. So first step you always need to do before you even think about the formula is bring all the units to one specific unit system. If it is given in meters per day, convert it to meters per second. If it is given in millimeter, convert it to meter. So always bring it to meter per second and meter. And then in the end, the diameter of the particle, if you're getting the answer, you will get the answer in meter, that you have to convert to millimeter, and that will give us the answer. So that's all for today's class. If anybody has doubt regarding the slides that I've taken in the session, you can ask. Otherwise, you're free to leave the session. So I'll be here for another 5 to 6 minutes. So if anybody has any doubts, you can ask, or we can wind up the session. Okay, Kiran, see you then. Thank you for attending the session. Bye-bye. Good night. Okay, thank you for attending the session, Vijay. Hope you have a good weekend. Okay, so I'll be ending the session now. Thank you for joining the session, and see you same time next week. Bye bye, and all of you have a good weekend. Thank you.